Hi, everyone. Welcome back. Can you hear me? Great. Okay, I'm very happy to introduce our first keynote speaker, Professor Lior Wolf. Professor Wolf is a professor at the School of Computer Science in Tel Aviv University and a research scientist at Facebook as well. His work has received numerous awards, including Best Paper Awards at ECCV in 2000 and at ICANN in 2016. Professor Wolf's work focuses on areas such as computer vision, deepfake detection, speech and audio synthesis, and deep learning. And today he will be presenting deep audio conversion technologies and their applications in speech, singing, and music. So let's welcome our speaker.
Thank you very much. So let me just share my screen and start. Okay, thank you. So actually just a small correction. I left Facebook AI Research a short time ago. But much of the work that is going to be presented was done at Facebook AI Research. So I'm going to speak about audio conversion. I'm going to show examples in music, then in singing, then in voice. And then I think I will describe some recent generation architectures that I think would be of interest to the audience. So let's start with music. And this is a work done at Facebook AI Research together with Noam, Yaniv, Adam. And the goal of this work, is to convert from one music domain to another. So basically, we would like to convert between two musical domains without having any notes. And we would like to work on instruments we haven't seen during training. So this is a major thing in our case. We would like to train on a few musical instruments or musical domains that we have training data for. But then on test time, we would like to get any musical instrument or any musical domain and convert it to one of the domains that we saw during training. And when we are talking about domains, we're not specifically talking about single instruments. We're talking about complex domains such as music, orchestra music by Mozart, or a choir singing Beethoven. So we are talking about complex domains with all the involved instruments. We model them at once. So how can one perform such a task? And let me just give credit to QuasiMuse, which prepared a presentation that I'm using some of the ideas and slides from there. So one can think that you can take the input music and you can then transcribe it, get the notes, and then use some sort of a synthesizer in order to create the output music. So this is something that you can try. The most problematic aspect of it is that the transcription tools are not very accurate, especially when there are multiple instruments playing at once. So it's not something you can use. You can think that maybe you want to use machine translation as an approach. So you would take something like an English to French translation. There would be music from one domain you insert, then you stop, and then the machine plays the second domain. The problem is that in order to train such a system, you need parallel corpus. So you need the ability to have supervision. What we do in our work is that we use an unsupervised approach. And this became very powerful, and it's going to be a theme throughout all the conversion technologies that I'm going to present later on. Most of them are using unparalleled data in an unsupervised approach. The basic building block that we use as the starting point of our method is the autoregressive model called the WaveNet autoencoder. So the WaveNet autoencoder by Google is basically a CNN that is the WaveNet encoder. So it takes the audio and then it encodes it, and then it creates a latent vector. And then this latent vector is being used to condition an autoregressive process. So by an autoregressive process, we mean that the next frame of audio is being generated based on the previous frames and based on the conditioning signal. So every time you create one frame of audio and you continue. So this is the autoregressive autoencoder. That is the basic building block that we use. In our case, you can think that we have a domain, let's say a piano, and then we encode it as a vector. We take this vector, we decode it, and we get back the music. So this is an autoencoder as it applies to a single domain. In our case, we would like to have one encoder, but multiple decoders. We would like to create music in the first domain, create music in the second domain, and so on. So we can take any musical instrument, put it through the encoder, and then get back any one of these domains. So in order to make a conversion, we can take the drum through the encoder and maybe convert it to a saxophone, just as an example. We would also like to have the ability to model unseen instruments. So we've never seen a flute in our training set, but we would like to use the encoder and then output it in each and every one of these domains. So this is why we call it a universal translator. It can convert from anything to any domain that we saw during training. So the number one problem is that if you try to achieve this task, basically use one encoder and multiple decoders, then most of the time, the encoding would be separated in the latent space based on the domain of the sample. So you would get the guitar samples over here and the piano samples over here and so on. So what's the problem with this? The problem is that the encoding has the information about the musical instrument. When you convert it, it's not able to use this information anymore. So we would like this latent space to be invariant to the actual musical domain. We would like it to be like a musician that perceives it in general terms, not in a domain-dependent terms. So the enemy here is exact memorization. We don't want the system to be a vocoder, basically just to compress the audio and then to output it. We want it to learn the underlying musical principles. So the way that this is done in our system is using adversarial training. So adversarial training basically means that we try to distinguish in the latent space, this is the latent space, we want to distinguish between the different domains. So we have a classifier, which is also called the domain confusion network, that tries to guess which domain is the input domain. So the domain confusion network, tries to distinguish between the different domains, but the encoder wants to create a unified representation. So the encoder wants the domains to look similar to this domain confusion network. So this is adversarial. The domain confusion networks wants to make the distinction. The encoder wants to make them all look the same. So this is one technique we use. The other one that we use in order to increase the generalizability of the system is that we distort the input. So you can see the inputs over here. We apply a random process and create an augmented version. The augmentation in our case basically means that we cut out slices of the audio and then shift the pitch by a random number. So we get this distorted sample, and then we require reconstruction to get the original sample, not the distorted one. So the system has to understand what's the underlying principle behind the music, and then we create it. And this is actually going to be a common theme also when we move to voice and to singing. So if we look at the loss functions that we use, there are basically only two loss functions. It's actually fairly system. One is the reconstruction loss. So reconstruction means that we take this trumpet, we encode it, we decode it as a trumpet, we get this one. The only slight difference is that we apply this augmentation in order to get a distorted signal. The other loss is the domain confusion loss. Basically, the encoder wants this loss to be as high as possible. It wants the domain confusion network to fail. So during inference, what we can do, we can take the drum, we can encode it, we can decode the drum, and we get the drum. This is what we did during training, but we can do more. We can encode the drum, get the latent representation, then decode it, and get each and every one of these domains. And what we can also do is to take an unseen instrument and then encode it and decode it to each and every one of these domains. So this is the universal aspect of the work. So let's hear some samples. I'm not going to play everything, but let's start. It's very important that you hear. All different output domains. This is singing into instrument. Completely out of the training domain. This is the conversion. This is somebody hitting the piano on the left side. This is me whistling. Let's stop here. So this is the type of conversion that we were aiming at. And it was pretty convincing much of the time. So before we move to singing, are there any questions up to this point?
Just to be sure we're on the same page, so you said that you're going to do instruments, but this signal instruments.
So actually, every domain here is has multiple instruments, right? So the orchestra has multiple instruments, and each one of the other domains is also multiple instruments. So it can work with, when I'm whistling, we can call it a single instrument, or when I'm singing, you can call it a single instrument, but it can convert from a single to many, from many to many. So it's not limited to a single instrument. The reason that I emphasized it is because I'm just showing for illustration an icon of a single instrument, but it's actually a full complicated domain. Basically, a domain was a CD from basically a domain was defined by a single CD in this case. Yes, please.
In fact, my main question is about evaluation. Of course, it looks nice, despite the fact that sometimes it's fading. First is objective evaluation. If you take two instruments where you play a score, not an orchestra, but you have a piano and a flute or so and so on. So you can verify that the notes are identical. So did you perform this?
So we actually did a series of evaluations. I didn't present the evaluation in this slide, but we hired musicians online on a freelancer's website, and we got them to convert the music. And then we asked both experts and amateurs to first identify what is being converted to what, and second, rate the naturalness of the audio. And the system did pretty well. The system actually has an advantage in this regards because it converts the audio directly and not through the notes. So it sounds more similar to the input. So it's always a problem of evaluation when you create generative models. We saw it earlier as well. We think that, as you said, there is room for improvement. The results are convincing, but still it's something that is a nice step. Let me just say that after this system, there was a system by OpenAI called the Jukebox. Excellent performance. The main difference from our perspective is that we were very limited with regards to the amount of data that we could use, just due to legal reasons. OpenAI just didn't care. They just took the entire internet as their training data set. And I think music AI has come a long way, and it's really exciting what is going on over there. And let's continue. So I'm going to move toward voice, but let's go through singing first. So we had this system, we wondered whether it's going to work for voice. So actually tried it for voice, and we converted between different singers, and it was lots of fun, but we thought we could improve more. At that time, we really couldn't use any free music, any licensed music anymore, so we had to rely on academic benchmarks. So what you're going to see is what we did with academic benchmarks. So the goal in music, in singing voice conversion, is basically one person is singing. We would like to take the voice of another person and make them sing the same voice, the same song, sorry. So this is also unsupervised because you cannot find two singers doing exactly the same song in exactly the same way. We are not going to use lyrics or phonetic features or matching samples. And unfortunately, we have very small data sets. So this actually pushes us into some innovations that I'm going to present. So it's not that bad. So the architecture that we are going to use is very similar to what we saw before. Actually, it's the same encoder and the same decoder and the same domain confusion network. But we're also going to use a lookup table that would embed the speakers. So every speaker is embedded in one vector. Every singer is embedded in one vector, 64 numbers that represent that specific singer. If we shift this vector, we shift the identity of the singer. So the system basically gets the input samples as J. J is the index of the singer. There are K different singers. The encoder is denoted by E, the decoder by D. And if we condition the decoder on a specific singer, we use this bracket annotation. And the domain confusion network is C, and every speaker is embedded in this vector space as VJ for singer J, which has dimensionality of 64. So when we train such a system, it's not easy to train, but mostly because we had very limited data. So we train it in two different phases. The first one is similar to what we saw earlier. The second one I'm going to talk because it has some nice concepts that can be used in voice and are being used in voice. So we will describe them. So the phase one is basically a construction loss. We start with a sample, we encode it, we decode with the decoder conditioned on the same singer, and we get a sample. Then we compare these two samples. How do we compare? We use the cross entropy loss. So in WaveNet architecture, you get discrete outputs. You can use the cross entropy loss to compare. So the network C, which is the adversarial network, the discriminator or the confusion network, tries to distinguish between the different singers. So it takes a sample of the encoding of a singer J and tries to classify it as singer J. This is the cross entropy loss. And the entire architecture, the encoder decoder, what they're trying to do is to reconstruct. This is the construction. And this is increase the domain confusion. So don't let the domain confusion network know which is the original singer. This is similar to what we saw before in the music. So we're able to reconstruct, but we didn't teach the network to actually perform translation. So this is where the music work ended. Now we're entering phase 2. So I'm going to talk about a very useful technique that is always used in augmentation. And it's very powerful, whether we're using images, whether we're using text, whatever we are using, it's a very powerful technique. It's called mix-up. So what does mix-up do? Mix-up takes two different examples. In this case, the example of one speaker and another, and tries to combine them. So in our case, what we do, we actually combine the embedding, not the samples. So this is mix-up in the latent domain. It's different, but it's motivated by the same idea. So we take, let's say, this singer.
I dream I held you in my...
And we mix it a little bit with this singer.
Love me tender.
Sorry. And we would like to create the first song in a voice that is in between.
I dream I held you in my arms when I awoke.
Is kind of a mixture of the two voices. So here comes the problem that we had earlier, that we actually had in the first session. When I'm talking about a mixture of two voices, it's not easy for us as humans to understand what it means or to evaluate it. And I see that Bence agrees with this. This is the major problem. Also in voice, if I take a male voice, convert it to a female voice, or take a French voice, convert it to an English-speaking voice, it's not easy to know how it would sound like. We can only guess, but it's not like images. In vision, it's very easy. You can take a male face, turn it into a female face, no problem. Everybody would know this is the female version of this person. This is the old version, the young version, the different ethnicity version. It's very easy to know. In voices, we don't have this capacity, but it doesn't really matter. All I want to do is to create these meshed voices. And then, so basically I take this mix up and I create a new singer just by taking the vectors in the latent space and mixing between the two, where there is a mixing coefficient that is sampled uniform. So what is this good for? What can I do with it? Because I created this new voice, new identity, but I don't have the ground truth for this identity. So the question is how I can use this sample. And the answer is that I can actually use what is called back translation. So what back translation is another very useful technology. What it means is that I don't have the target for this generated sample. This is the mixed sample, mixed between two different identities. I don't have the ground truth for it, but I can use it as a source sample and convert it to another identity that I have the ground truth and then compare the ground truth. So this is called back translation. It's used a lot in NLP, also another useful technique. So phase 2 is about using mix-up and back translation. And it's also about using an augmentation. So we had very little data. We had to do anything that we could. So we had like 4-time augmentation in the following way. First, we know that when a signal is played backward, the identity of the speaker is the same. So if you take an audio, I didn't bring a sample, but you play it backward, you can identify the speaker. It's not a challenge. So we just doubled the data set by playing everything backward. And then from the computer point of view, if we just take the numbers of the audio signal in the time domain, and we just take the negative of them, multiply by -1, then it's going to sound exactly the same to the human ear, but we just obtained another training sample. So just these two tricks to increase the data set a little bit. And then the experiments, we had 2 small data sets, 2 publicly available data sets that we used, and the NUS and the dump. And we used the usual metrics, mean opinion score for the quality, mean opinion score for the similarity. And also we trained the CNN to distinguish between the different singers and wanted to see if we can identify. And we can see that when we convert, it's slightly worse than when we reconstruct, but the scores are pretty reasonable. They scale from 1 to 5. And for similarity, conversion is worse than reconstruction. This is expected, but still it's more than 3, maybe 3.5, depending on the exact experiment. And we use recognition as an ablation study. So if we only train phase 1 and we look at the generated converted sample, then we get around 60% recognition of the target speaker. If we apply phase 1 with augmentation, but without phase 2, then it improves. If you apply phase 2, but don't use any mix-up, it improves further. If you use the full method, it improves even further. So phase 2 without mix-up means that we do back translation, but between the existing singers. So let's hear a few samples. I don't want to get your expectations too high. It's a very small data set, but let's say
I have a dream.
This is the destination singer. And this is, sorry. And this is the converted one.
I have a dream.
So it does convert somehow. It's not where we want it, but remember it's a smallish data set. So this was one work that we did in converting singing voices. Then we did another one. And the goal of the second one is a bit more extreme. The goal of the second one is to take somebody speaking and then make them sing. So again, it's unsupervised, no parallel training data and so on. It has the added capability of cross-domain between speech and singing, and it's any-to-many. So we can synthesize each and every speaker in the training set, but the input can be from completely different test set, from speaking voices that we never saw during training and so on. So the method here is slightly more sophisticated. It doesn't train the encoder from scratch. It's using predetermined signals. And in this case, it takes the waveform and it uses 3 different encoders that are not trained, that are available. The first one is basically trying to understand what is being said. I mean, in this case, being sang. So what is the text, the underlying text? And for this, we use a WAV2-letter network that is not the most recent or most powerful speech recognition. It improved a lot since then, but the version that we used was slightly outdated, but still good enough to create speech features. And the other one is we use a network that was trained to extract pitch and melody, and we used it. This is the second encoder. We use it to get the melody of the song, and we also get a signal for the loudness. And then we concatenate these 3 together, and we feed the generator, and we generate the output. So the generator here is not autoregressive. It's another architecture. We'll talk about it in a second. So it's much faster, and we can apply multiple losses that are harder to apply in an autoregressive network. So, but actually I have slides about all of this. So let's start. The loudness basically measures what humans perceive as the loudness of the audio. And we discussed loudness before in the first presentation this morning. In music, of course, it also plays a role. This is the speech-to-text network, WAV2-letter. Gives us a kind of a perceptual loss on the audio that we perceive. We would like the intermediate activations of this network to be the same between the original audio and the output. So this is a perceptual loss. And there is another perceptual loss that comes from a network that was trained to identify the melody. pre-trained to identify the melody by Kim et al. The decoder architecture is what is called a parallel wavegun. So we shifted from the WaveNet autoencoder to a parallel wavegun. Basically, it's a framework that takes a random noise as input and then creates an audio. And the audio is being measured by multiple signals. One of them is the discriminator that tells whether this audio sounds the same as the input samples. And the other one is a reconstruction loss that is the multiscale STFT. So the STFT loss looks like this. We are going to use it multiple times. It's actually very useful. I'm going to present 2 works here that are using it. There are other projects that we use the same loss. It takes the short time Fourier transform of the signal and the recreated signal, compares them using the F norm, and also takes the log and compares it with the L1 norm. And it's done for multiple scales. And these are the scales that are being used, multiple window sizes for the STFT. And then it's all summed up across all different scales. So to summarize, the training schemes looks like this. We have the generator loss that tries to fool the discriminator. This is the adversarial term over here, tries to reconstruct the same sample input, the same sample is being generated. This is reconstruction. There is the perceptual loss for the melody and the perceptual loss for the content, which is also very important. And we are going to use it a lot also in voice later on. And the discriminator, of course, tries to tell us that this is a fake sample, not a real sample. So this was for one singer. If there are multiple singers, then we have as input one singer, as output another singer. We can no longer use the reconstruction loss. We can use mix-up and back translation as we used before, which we actually do. So in this case of the unaligned case, we still have the discriminator and we still have the generator, and we have the WAV2 letter loss, because after we convert, we want the same thing to be saying the same words. And we have the loudness. Let me get this out of the way. And we have the loudness score, and we have the melody, but we don't have the reconstruction. And back translation, just as before, we create a mixed identity, and we use back translation on this. So this is the case in multi-singer, just combining all the losses that we described earlier. So let's hear a few samples. And in this case, the source
Dashing through the snow in a one-horse
is singing, but the target voice is speaking.
The increase of bank for
And the conversion
dashing through the snow
sounds
in a
like
one-horse
this.
open sleigh, o'er the fields we go, laughing all the way.
It's better than the previous work. The main reason is that we are using pre-trained networks as encoders. So we're doing some sort of a transfer learning. Let's see if the second example sounds as good.
Edelweiss, Edelweiss.
Slow burn, no sleep, show.
And this is the conversion.
Edelweiss, Edelweiss.
So it does perform something of the sort that we would like it to do. And we are quite happy with the results. So before I move on to voice, are there any questions up to this point? So let me think about it for a second. So the answer is actually very simple. We use pre-trained encoders, so we don't train the encoder. So there's nothing to train with the domain confusion network. So the embedding that we obtain in this case, the one that conditions the generator, is basically used on 3 different networks that are trained for other tasks. We are not training it as part of the system. So no training takes place that can be influenced by the domain confusion network. So the question is, why won't you add to the concatenation of the 3 embeddings a few more trainable layers and then add the domain confusion network? This is something that can definitely be tried. Yes, and there's another question. Yes, please.
My question is that speech needs a frequency band up to 12,000 hertz or higher, and the music needs only for 2,500 hertz. And as I heard in this example, what is the situation with that fricatives, which are in speech normally have about 6,000 to 5,000 hertz, and here in CD they
Okay, that's a very interesting question, and it talks about the frequency that is being used in speech, which is much higher than the one that we need in music. So the question is, how would these frequencies influence the result if you're converting a speaking voice to a singing voice? And unfortunately, I don't remember the frequency that we used in music, but it's probably lower and not higher. And our goal is to create something that is recognizable as the person. We don't want to capture all the frequencies of the voice. We want it to be recognized as the speaker, as the specific speaker. And your idea would be actually very interesting if we go back from singing back to voice, then all these frequencies that you care about in voice would be lost. So this is indeed a limitation that we should think more about. Okay, let's see if there's something. Okay, so did you need to normalize or scale the F0 for different speakers? So we did not. This is an interesting suggestion. So you would still have the variation in time, but you would normalize it. It's an interesting thing to try. We didn't try it. Thank you for this question, Dan. So let's shift the focus to voice and consider a few applications. So voice conversion. So voice conversion is basically, converting one voice to another. I don't need to play the sample. And we came up with something that we call TTS skins. What is TTS skins? Basically, it's a voice conversion by a different name, but it's for the application of using a robotic voice and then applying skins and converting it to any voice. So the goal is to generate, using the same robotic voice, multiple voices where the skins are applied very casually. So we just take some speaker and very quickly train on this voice and create a new voice. So it's about, skins is about being able to do voice conversion casually, quickly, with a few training, with a very short training sample of the new speaker. So in this case, the architecture is an autoregressive one. We use the WAV two-letter encoder that we saw earlier. We use a lookup table for the speaker to model the speaker, and we generate the audio using an autoregressive model. So training is being done based on the signal that is the encoding with the WAV two-letter of the input and the embedding of the speaker and the F0 of the input signal. And from this, we reconstruct the sample. This is the reconstruction loss that is being used. So with this regards, it's simpler than the other systems. I'm not presenting the work in the order in which the work were conducted. I'm presenting by topic. So this is a bit earlier. It's a bit simpler. We use only this specific loss, the reconstruction loss. What we would like to focus here is about fitting a new speaker. So this is actually something that is important, and we see it again and again throughout our studies. If you want to fit a new speaker, you can just try to find a better embedding. So just change the embedding vector V. So this is something that you could do, but it's actually not ideal. If you don't fine-tune the decoder, you are not going to improve the system. So you need to find the best embedding. So you start with the most similar speaker, and then you also fine-tune the embedding, and then you get the best results. We used 5 minutes of the new speaker in order to fit the data. It's actually very quick to fit the data. You don't need to train for a lot of time, it's just fine-tuning. So here again, I don't want to get into all these details. We had 2 different data sets. As subjective measures, we used the mean opinion score. We had an objective measure for the reconstruction, and we also had an automatic speaker identification. So whenever you have multiple identities, the ability to identify the speaker is an important signal that can be used. So actually, I don't want to go through all these baseline. Believe us that it's better than a competition. Also in the voice conversion challenge, we applied it, of course, after the challenge, not during the challenge, but we compared to the top systems, and we were able to obtain same level of results or better in the voice conversion challenge. Let's play 1 or 2 samples. So.
In another moment, down went Alice after it, never once considering how in the world she was to get out again.
So this is the source, this is the target voice.
In another moment, down went Alice after it.
This is the conversion.
In another moment, down went Alice after it, never once considering how in the world she was to get out again.
So this is one sample and so on. So this is about conversion. I'm now going to speak about something else that is highly related. So basically a very similar architecture, but is used to what we call speech regeneration. Speech regeneration is the ability to take an audio sample and denoise it by taking the elements of the voice and then recreating the voice. So if you think about traditional denoising systems, they care about the noise, they try to remove the noise. We say, okay, this is nice, but we actually want to make sure that the voice itself is high quality. So we would like to take all the components of the noise, of the voice, and take these components and reconstruct the voice. And the motivation is that we would like to have some sort of video conference application that is invariant to the background noise, not by taking the audio signal in and trying to clean it, but by taking all the components that are important for recreating the voice, take them separately and combine them together. So this is the architecture that we used. So we start with 16 kilohertz noisy recording, and we generate 24 kilohertz of high fidelity recording. And the components of the system is first, we use a state-of-the-art denoiser, also by Facebook AI. Just take the input, try to remove all the noise that you can. This is the first one. Just as a first step, we do perform denoising. Then we extract speech features. This is the same features as you saw earlier, the WAV2-letter network. We also extract the F0 signal and the loudness of the audio. And then we add another input vector, which is the D vector. basically a vector that is used in speaker recognition system to encode the speaker. And then we use a different architecture, not the one that we saw before, not the parallel waveguide, not the wavelet. This architecture is called GAN TTS, was published by others in Europe's 2020. And it basically employs a GAN and another trick that I'm going to show you in a second. So the GAN, as usual, there's a discriminator between real and fake. Nothing surprising over here. The other thing is that the multispectral loss is being used, the one that we saw earlier with the STFT, but it's going to be used in a different way. In different ways called spectral energy distance. So this is the idea that is behind GAN TTS. You take the difference between the target and the generation for one random vector, the difference that you get for another random vector. So you just sample the output twice with two random inputs, but then you subtract the difference between those two signals. So you would like to actually encourage the system to create a variation based on the random vectors. You encourage the system to sound a little bit different whenever you change the random vector. So this is the main contribution of this generation architecture. Training objective is similar to before. You have this reconstruction loss with the STFT with the extra element for difference between two different random samples. You have the adversarial training objective and you train it. And we have some benchmarks to show that this is actually performing well. Also, both automatic and measures that are based on the activations of the ASR network and a mean score type of evaluation. We compare to different systems used for denoising, and it works pretty well. I don't want to get into all of these details, but let's see this demo that was presented. And actually, I must say, this is an online demo in a browser, but there's a GPU in the background. And this was prepared, this demo by Ori, but an earlier version of this type of demo was created by Roy, who sits right over here when he was an intern at Facebook AI. So if you'd like to know how to create real-time demos that convert speech with very small latency on the browser by connecting to a GPU server, Roy is the person that you would like to ask.
So yes, just for comparison, you can now hear me again with the reverb and standard room acoustics. And if I wish to improve that, I will just now switch to the model's output.
Yes, so I can read some text. And for instance, when ready, press the start button and start speaking to your headphones microphone. You'll hear yourself with an enhanced speech. Thank you.
So you can basically clean the voice in real time with very little latency. So, so before I move to the next topic, which is completely different, but I would like to present it because I think it has a lot to do about where we are going to go in the future. Are there any questions? Okay, and let's see if there are questions from the Zoom audience. Okay, so I'm going to move on. Okay, so I would like to talk a little bit about what is called diffusion models, because after all, it is a workshop, so I would like to let you know what we are, type of models that we invest in right now. And I think this is a very important advancement in generation. that not everyone is aware of, is very useful in speech, very useful in vision. And we talk about WaveNet, and we talked about parallel WaveNet, we talked about GAN TTS, all very good models. We believe that with diffusion models, you can get even better results, but they have limitations, and I would like to discuss them a little bit. So this is joint work with Elia and Robin, unpublished, but still interesting. So what is the idea between diffusion processes? Well, if you take a signal, this is the clean signal, and you add Gaussian noise to it, and you add Gaussian noise, at the end you would get some Gaussian noise. So you can get from the clean to the noisy. This is called diffusion. You can actually think about going in the other direction. So you can train a neural network that goes from the noisy and then to the less noisy and to the less noisy until it gets to the input. So this neural network is maybe conditioned on some signal. It wants to, maybe it's conditioned on text, for example, to create speech. But in essence, it clears the noise little by little. So the point is that you can train such a network, because going from here to here, you created yourself a training sample. You just need to go in the other direction. So this is kind of a Markov chain, both in the denoising and in the noising. You just look at the current situation and you estimate how would it look just with a little bit less noise. What would the signal look like? And you can start with a complete noise, random noise, and get all the way to the clean input. So there is this network that looks at the data and tries to estimate what would be the next step of denoising. And it gets a parameter. The parameter is the noise level. And this parameter in most systems is something that is predetermined. There is a grid search for the optimal parameters, but then you want to be very conservative. Just clean a little bit at a time, just little by little. So what we propose in this work is, instead of guessing this parameter or predetermining it, is to look at the signal itself and estimate this noisy parameter. And the hope is that if we do this, if we train a neural network to find the denoising parameter, then we can make the denoising process faster. So we can be less conservative about denoising, and we can make maybe in 6 iterations instead of 1,000 iterations. So this is the system. We get the noisy signal, we apply the network that estimates the parameter of the denoising, we get it as input to the network that predicts the next signal, we create the next sample, and so on. So I wouldn't go through the numbers, but basically this is a system that goes for 1,000 iterations. This is a system that goes for only 6 iterations. This is our method for 6 iterations. In most of the more important metrics, we are better. I hope I could make something more, a stronger statement, but this is the case. We will hear samples in a second. And this is just for 6 different iterations. The task is to take the mel spectra and convert it to audio. So you can imagine that the mel spectra is being generated by a text-to-speech system, and then you convert it to audio. This is the task over here. You generate audio conditioned on the mel spectra. So in essence, this is the
has reached the age of 70.
This is what you get with the best weights you can use a grid search to find for 6 iterations.
Has reached the age of 70.
And this is what you get with our system.
Has reached the age of 70 and does not avail himself of the opportunity to retire on a pension.
And there are other, so this was one contribution that we made in the diffusion methods. And the other one is in diffusion models. And the other one is that instead of using a Gaussian distribution, we actually tried the gamma distribution, and we tried the Gaussian mixture model instead of a signal Gaussian. We think both of them better fit the data, and we can get better results
The Commission recognizes that no set of meaning.
This is the competition.
The Commission recognizes that no set of meaningful
This is
criteria.
our with gamma distribution instead of a Gaussian distribution. And this is ours with a mixture of Gaussians, each of which needs to be derived independently. It's not very easy to plug in. So let's.
The Commission recognizes that no set of meaningful criteria will yield the names.
Okay, so those are the kind of results that we obtain for such models. Let me just say, whatever you hear in this case, we also have examples for images using exactly the same technique for generating images, not audio, reinforcing the improvement that one obtains with our variants of these diffusions models. Any questions up to here? So it's actually already on archive, both papers. We just didn't publish them. They're still being reviewed, but you can find them on archive. The very, very latest, what we're doing right now, I will share at the very end. Any other questions? Sorry, just. Okay, so the question is, why limit to 6 iterations? So we just took 6 as a number that is very low in comparison to 1,000, because usually to get very good quality, you go to 1,000. We said, okay, let's see if we can do with 6 and obtain almost the same quality. So why gamma in the mixture of Gaussian seem to be better than the Gaussian distribution? So there's work actually in computer vision that shows that modeling with Gaussian is not ideal because the distribution is not symmetric and other factors. So we can motivate based on these. It's very hard for real data to make any assumptions on the data, but we can see with fitting experiments that fitting with the gamma distribution works better than fitting with the Gaussian distribution. So let's conclude. So we discussed mostly convergent technologies as they are being used for music, for singing, and for speech. And then we also spoke just a little bit about speech enhancement. And then I gave you some window into the exciting world, I think, of diffusion models that I think are the future of generative models. And if you would like to discuss what we are doing right now, so 3 sample projects. So one project that we are doing is speech separation using diffusion models. It's actually able to improve considerably. It's not as easy as it sounds. It's not enough to recreate the output with diffusion models. This is actually the small part. We are doing much more than this. And we're able to get much better qualities for many more speakers. So imagine speech separation. We have some contributions. I didn't bring them into the talk. It's already overcrowded, but you have multiple speakers. You have 1 microphone, 1 recording. You would like to separate 2 different speakers. Current systems work kind of well for 2, 3, maybe 4 speakers, especially on synthetic data sets and real data sets. 2 speakers is also plenty, is already plenty. With this kind of technology, we want to push the ability to go to 10 speakers or more. And there is a work that we are doing that actually is similar in the spirit to the work that we saw last about the location effect in mean opinion score, but we would like to do it in an automatic way using explainability methods and help debug models this way. And the last thing in music, we are trying to build synthesizers to fit any instrument that you can hear from from single samples. So this is basically what's keeping us busy in the domain of audio. So thank you very much.
Thank you very much for the nice talk. Our next session is the morning session discussion, so we can move on to that next.
Yes, please.
So it's a general question for you. When you are doing conversion, one parameter which is always ignored is tempo. So you keep, in fact, the tempo of a source signal.
Yes.
But as you know, tempo is a characteristic of the speakers. It's a characteristic of the instruments. For example, for trumpets, you need to breathe. You don't need to breathe when you are playing piano. So what is your...
Yes, this is an excellent question. And we actually had a work done exactly on this. We used something that is similar to the wavelet autoencoder, but we added an attention mechanism in order to make different timing. And I must say, we were very proud about the technology, but it's hard to train and hard to evaluate whether you get a real improvement. So we check the box on this requirement, but what is the real world effect? Unclear at this point. But using an attention mechanism, we were able to address it. I just didn't include it in the presentation.
Thanks for the excellent talk. And now here we have lunchtime and session discussion. So those who want to discuss right now can start to discuss, but then maybe they will have less time for lunch. So for those who are present, I recommend to go for lunch. And then if you finish earlier, then you can join on a spatial chat for the discussion. So for the rest who are at home and who have just a sandwich quickly, then I recommend to go to spatial chat and maybe while eating their sandwich, they can also have the discussion. Thank you.